Good morning, I am Isabella Ziccardi, and in this talk I will present the paper Parallel Load Balancing on Constrained Client-Server Topologies. The authors are Andrea Clementi, Emanuele Natale, and me, Isabella Ziccardi. First of all, I introduce the load balancing problem. This problem is settled in a client-server distributed model. We have the set C of n clients and the set S of n servers. These two sets are connected via a fixed bipartite graph G. Each client V has a fixed number of D of requests, and this request must be assigned to the servers. In this talk, I will always represent requests as red balls, and I will often call them ball. Each client V can send its request only to the server in its neighborhood N of V. The goal of the load balancing problem is to find a protocol that assigns every client request to some server. And this has to be done in order to minimize the maximum load of the servers, where the load of a server is the overall number of requests assigned to it. The load balancing algorithms have been the subject of a longer and active line of research, and the studied algorithms could be centralized or distributed. And in this talk, we always assume the underlying graph G to be bipartite and delta regular, but I noticed that delta regularity in some work can be partially relaxed. If we express the degree delta of the graph as a function of n, we can identify three main cases. When delta is equal to n, we have a complete graph. When delta is a linear function of n, we have a dense graph. And when delta is a sublinear function of n, we have a non-dense graph. In this table, we try to summarize the previous main work on this problem, and we classify them according to the degree of the graph G and to the type of the algorithm. As we can see in the table, there are no previous work about a parallel algorithm which solves the load balancing problem with a non-dense underlying graph. So when the degree of the graph is a sublinear function of n. So our algorithmic goal is to design an efficient and parallel load balancing protocol for non-dense client-server topologies. So we have a graph G regular with degree delta, where delta is a sublinear function of n. We motivate this setting by some possible application. For example, a client may decide to send requests only to a subset of trusted servers, or alternatively, clients and server could be placed over a metric space, so the interactions are restricted by proximity constraints. In our work, we decided to adopt a standard synchronous distributed model. In this model, client and servers are autonomous computing elements, and they can exchange messages in synchronous rounds over the edges of the graph G. We call our protocol SAER, which is an acronym to Stop Accepting If Exceeding Requests. Our protocol is a variant of the protocol RISE of Becchetti et al., presented in the conference SODA 2020. Our protocol, SAER, has two input parameters. The parameter D represents the number of requests of each client, and the parameter C determines the overall maximum load of the servers. In this slide, there is the pseudocode of the protocol, but due to time limits, in this talk I will not read it, but I will explain it in a simpler way with some animation. Therefore, if you want to read the pseudocode carefully, I suggest you to read it in the paper. The SAER protocol works in rounds, and each round is divided into two phases. Here, I describe a general round of the protocol. In the first phase, each client V, for each of its remaining balls, chooses a server uniformly at random in its neighborhood and submits a ball request to it. In the second phase, each server U becomes burned if it receives more than C times D balls since the start of the process. If a server is burned, it rejects all the balls received in the current round. If a server is not burned, it accepts all the balls received in the current round. And notice that so each server never accepts more than C times D request. If all the balls of a client V have been accepted, V gets into the final state done and terminates the protocol. Terminates when all the balls of every client V have been accepted by some server, and so when all the clients get into the state done. So for example, in the picture, the protocol is not terminated, since there are some clients that are not into the state done. So the protocol continues until all the requests of each client will be accepted by some server. About the analysis of SAER protocol, in the paper we proved that this one theorem. The theorem states that if we have a graph G such that it is bipartite, where the set of the nodes is composed by n clients and n servers, and where the degree delta is a linear function of log square of n, and notice that delta could be also much smaller than n. And if we have any constant d, which represents the number of the balls of each client, then a sufficiently large constant c can be fixed such that the SAER with an input c and d on the graph G has c times d maximum load, log n completion time, and n overall work, where the overall work is the total number of exchanges messages. The claim 1 of the theorem states that SAER has max load C times D. If the protocol terminates, then the claim is trivial, since the servers in the protocol never accept more than C times D balls. The major technical results are the claim 2 and the claim 3 of the theorem, which state that SAER has completion time of log n and overall work of n. So, to solve these major problems, we observe the SAER process at every round T of the neighborhood n of V of any fixed client V, and we look at the overall number RT of NV of a live client requests that the neighborhood of V receives at each round T, and we ask how this quantity decreases as T increases. We look also at the fraction of burned servers in the neighborhood of the client V at each round T, so ST of V, and we ask how this quantity increases as t increases. So, our key idea is to express this two quantity in a crossing relationship, which depends on their previous values. We then express this relationship by some effective recursive formulas for their respective expected values. Then we show that such expected behavior of RT of MV and ST of V globally prove the claim 2 and the claim 3 in a mean field analysis. And finally, we provide concentration arguments to prove that everything works with high probability. The main theorem follows from that main lemma. This lemma states that the fraction of Bernard nodes St of V is always bounded by 1/2 without probability for all the rounds until time 3 log n. The proof of the main theorem follows from this lemma. Indeed, if we look at the probability that a single request of a client is not accepted in 3 log n rounds, we have that this probability is the probability that the request is always sent to a Bernard node. Since for the lemma we have an upper bound to the fraction of Bernard nodes, we have that this probability is bounded by 1/2 of the power of 3 log n, and so there is a negligible probability. To prove the main lemma, we have to find an upper bound to the fraction of Bernard nodes in the neighborhood of a client B. And since a node is burned when it receives more than c times the requests since the start of the process, we have that the fraction of Bernard nodes is bounded by the ratio between the number of the bolts sent in the neighborhood and V of the client V since the start of the process and C times D times delta. Then, recalling that RT of NV is the number of requests that the neighborhood of V receives at time t, we can write the equation 4 as in 5. Then, dividing the sum in the equation 5 into two parts, we get the recursive formula. So, the fraction of Bernard nodes in the neighborhood of V is bounded by the fraction of Bernard nodes in the same neighborhood but at the previous round, plus the number of requests that the neighborhood of V receives at time t over C times D times delta. So, there is the equation in sixth. St of V is bounded by St minus 1 of V plus RT of NV over C times D times delta. So, the next step is to find an upper bound on St minus 1 of V and an upper bound on RT of NV to get an upper bound on St of V by the recursive formula. In this talk, we will do only a mean field analysis, so we only give a sketch of our analysis considering only the expected behavior of the SAER process. So, we will omit the major technical issues due to the presence of strong correlation in random variables. For example, there is a strong correlation between the current alive requests in a given server neighborhood and the current burned servers in a given client neighborhood. Then, to prove the main lemma, we first bound the expected value of the number of requests that the neighborhood of V receives in the first round. And we prove that this expected value is bounded by D times delta. This implies that the expected values of the fraction of Bernard nodes in a client's neighborhood in the first round is bounded by 1 over C. and we call this quantity as 1. Then we bound the expected value of the number of requests that the neighborhood of a client B receives as a general round T, so RT of NB, in a general round T. We prove that if the fraction of burned-up nodes in the neighborhood of B at the previous time is bounded by St-1, then the expected value of RT of NB is bounded by delta times D times St-1 at the power of T-1. Then we apply the recursive formula, so St of V is bounded by St-1 of V plus RT of NV over C times D times delta, and we get that the expected value of St of V is bounded by St-1 plus St-1 at the power of T-1 over C, and we call this quantity St. So from these two claims, we get the fraction of burned nodes at time t is always bounded by St, where St is a sequence defined in a recursive way in 7. So S1 is 1 over C, and St is St-1 plus St-1 at the power of T-1 over C. We prove that if C is a large enough constant, then for all the time t, St is bounded by 1/2, and this proves that the expected value of St of V is bounded by 1/2. So this proves that the lemma works in expectation. To prove that everything works also with high probability, we apply some concentration arguments. So, in conclusion, SAER is a parallel protocol for the load balancing problem, and it works on delta regular graph with delta is at least a linear function of log square of n. The protocol achieves constant maximum load and has completion time of log n. So thank you for listening to me, and thank you for the attention.